Alrighty, osmotic pressure. Under pressure. So, sorry, that was really bad. So osmotic pressure is the last colligative property we're going to look at. So this is a tube with a semi-permeable membrane in it. So this means that it allows the passage of some molecules, but not all, based on size. So if you were to place a solution and pure solvent in the same container, but separate them, what happens is that the level of the solvent side would decrease while the solution side will increase. So what happens is that eventually it will be constant. Once the pure solvent is able to go through the semi-permeable membrane, it will eventually be at a constant pressure, if you will. So this is a process called osmosis. You probably heard of this in biology last year. So the difference between the two, this is the osmotic pressure. What can happen, for example, is that by putting this type of contraption, if you will, by adding the semi-permeable membrane, if I push this back through just adding pressure going this way, I can actually separate out from the solution. I can get back the solvent right here. So if this goes all the way down, I can get more solvent on this side, and that is actually something called reverse osmosis. And this is what they do to take out the salt or the sodium chloride from seawater to be able to drink it. All right, osmotic pressure is expressed by the following formula: pi equals I times capital M, which is molarity, it's not molality, times R, which we will use this later on as well in gases, times your temperature in Kelvin. Pi is pressure, unit is atmospheres. Van Hoff factor, so you should recognize that hopefully. Alrighty. What is the osmotic pressure of a solution prepared by adding 13.65 grams of sucrose, I give you the formula right there, to enough water to make 250 mLs of solution at 25 degrees Celsius. So pi equals IMRT. So I'm trying to find this one right here. Trying to find that. So I is my Van Hoff factor, and because this is a non-electrolyte, because it ends in ose, so it's a sugar, so it's going to be 1. Molarity. So I got to convert these grams into moles and divide by this volume, but I got to convert that to liters. So 13.65 grams, C12H22O11. Divide that by the molar mass, so that molar mass is going to be 12 times 12.01 plus 22 times 1.008 plus 11 times 16. So it's going to be 342.4161. So my moles is going to be 0.03986 ... I'm going to divide by my volume in liters because it's molarity, moles per liter. So it's going to be 123, so 0.250. Divide those two numbers, I end up with 0.159455 ... So I'm going to plug this number in here, 0.194555 ... times R. So R is the one in the front on the last slide, I'm sorry. So it's going to, I'll make that this color, 0.08206. And then your temperature, it's your last one. It's 25 degrees Celsius, but this is going to be in Kelvin. So 25 plus 273 is 298. There you go. So times 298. So then you do your work, you calculate. So 1 times the 0.159 times 0.08206 times your temperature, 298. So you end up with 3.89929647 Looks like we have 2 sig figs, because this is 2, 2, and this is 4, so let's make it 2. So this will be 1, 2, look at over here, so this will be 3.9 atmospheres. And box it in. I know that was a long slide. Osmotic pressure of human blood is 7.6 atmospheres. Okay. At 37 degrees Celsius. So there's my temperature, my osmotic pressure there. What is the mass in grams of sucrose is required to make 1 liter of aqueous solution if the solution must have the same osmotic pressure as the body temperature, blah, blah, blah. So let's look at it this way. We have osmotic pressure, pi equals IMRT. I am trying to find the mass. So I gotta, of all these things in here, the only thing that can get you mass is going to be your molarity. So I need to rearrange this equation to solve for m, first of all. So I got to divide both sides by IRT. So pi over IRT equals molarity. So eventually I have to get to grams from molarity, but first I gotta get there. So I'm gonna plug in my atmospheres for my pressure. It's gonna be over my Van't Hoff factor, which is going to be 1 because this is all still a non-electrolyte, times 0.08206, that's my R. Then my temperature needs to be in Kelvin, so 37 degrees Celsius plus 273, that is going to be 310 Kelvin. So I got to solve for molarity. So 7.6 divided by 1, so this part of parentheses, 1 times 0.08206 times 310, close parentheses, the answer is going to be 0.298755857, blah, 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 molarity. So I need to remember that molarity is moles per liter. So I want to get this by itself. So moles, number of moles is liters times molarity equals moles. So I plug in my numbers. So luckily, my volume is just going to be 1, so that helps. And then I plug in this number here, and this equals my number of moles. So 0.29875 moles. To convert this to grams, I need to multiply this by the molar mass, which I actually give it to you in this problem. So times 342.3 grams per mole. So after all that work, multiply this by 342.3, I will end up with 102.265, blah, blah, blah. Looks like we have 2 sig figs, so my answer is going to be, let's make it 100. Actually, just make it simple. 102 grams of sucrose, C12H22O11. Alrighty, very good. That was a lot of work, I know. People are wondering why, what's the point of this, etc. Well, think about this. Human blood and all that. It's important to get the pressures right, temperatures right, etc. because if you don't, and you're introducing something else into the body, it can cause problems if it's out of whack, if you will. And you don't want to do that. Alrighty.